Yeah, so really we're investigating and modeling linear associations. That pretty much sums it up to me. Once you've came back and you've sort of gone through most of this chapter, hopefully that will make a bit of sense to you. So we're trying to model data to fit a linear line. And that's what we really want to do. So we're going to investigate it and look at that and make predictions. So the idea with here is you're going to have a scatter plot. It's all going to be, scatter plots. And we're really going to be looking at how do we use a linear equation to make predictions from it. So, for example, we can make predictions, say, we fit this data, we do a lin reg, and this will be the line of best fit. We're going to understand how this line is calculated. We're going to look at that. We're also going to look at, so for example, if I had, a value of X here, what would be my predicted value? My predicted value would be there. If I had a value of, say, whatever my Y-axis was here, what would be my predicted value? My predicted value would be there. Then we'll look at things like, oh, well, if that's my predicted, what's my difference from my actual versus my predicted? So we look at these sort of things. Sometimes a linear model won't be best fit for you. We will find that you will actually need to do a transformation. So I'm just sort of going to skip a fair bit further down. So something like this, I mean, if you try and fit a straight line on this, you can kind of see that would be a straight line there, and it's not a really good fit for the data. You'd be better off putting a model that goes, curved. So we don't actually get into these curved ones. What we do is we actually transform these axes later on. So it might be like that, and we'll have a different type of axes, and then that will actually transfer all these dots to then become straight. And that's what we're going to look at. So we're going to look at nonlinear plots and then how we make them linear. And that's what we'll be looking at as well. So that's kind of where we're going with that. And then pretty much that's a big part. So really from 3D onwards, it's all the same kind of transformation thing. So what we're trying to do is we're trying to make these become linear by changing the scale on there. So 3D for the rest of the chapter is pretty much all the same. So it's about how we make it, or we call it linearize. So we're trying to make the data become straight. So really 3D, then we sort of got 3E. I'll just keep on going down here. Then we got like a log transformation. So we're talking about how we do log transformations, these ones. So if we, transform this axis to a log or the Y-axis to a log. And then we've got another transformation. Reciprocal transformations. Reciprocal transformations is just 1 over X or 1 over Y. So we're looking at how we actually, transfer. See how this data is curved here. So you can see how it's curved. And what we're going to do is I might change my X-axis to 1 over X, for example, and then that would then become, all these dots would then become looking straight. And then we do a lin reg to it. And all we do is, like, instead of writing Y equals mx plus c, once we've done the transformation, it'll be y equals m on x. It will then be y equals, I should just do that. So instead of y equals mx plus c, it will become y equals m on x, or m1 because of x, plus c. So you pretty much do exactly the same thing. We will cover that. And all these other sub-chapters, they pretty much just, they're all transformations. So 3D, E, and F are all just transformations. So really, it's a pretty quick chapter, I find this. So I think we'll pretty much finish this one by the time we go back to school. So square transformations is D. And what have we got? 3C is residual plots. So really, I see it as ABC, and then D is kind of like all together. Normally, D, E, and F would just be one sub-chapter in other textbooks, but they've just separated it here. So really just keep watching the videos with Ed Rollo, but I just wanted to go through just a couple of things because I do like the way I sort of go through it rather than sort of Ed Rollo when I did watch those videos. I don't know if they've upgraded them, but from a little while ago. Just to talk about what a linear regression line is, and we call it a least squared regression line. This is a really important concept to actually understand what a least squared regression line is, because it does come up in a dot point in study design. You need to understand what the meaning of it is, because it does come up in multiple choice questions. And if you actually understand why it's called least squares regression, It actually makes sense. So the one thing you've got to understand is first about these residuals. So these residuals are really, it's actual minus predicted. So the residual value is the vertical distance, or the distance in the y, the difference in the y coordinate between these two, between my actual versus my predicted. So these are the residual values. So clearly my residual value here is going to be negative. This one's going to be negative because it's actual minus predicted, and the predicted is a higher value because it's on the y scale. And this would be a positive value because if I, for example, let's just say this was like, I don't know, 5, 10, 15, 20, 25. This is 29. Let's just say this is 29. And, you know, my predicted is, what's that going to be, about 23. The difference between this is 6. So the residual value of this would be actual minus predicted, 29 minus 23. That would be 6, right? Here, if you look at this, we've got a predicted at 11 and the actual 11, and the predicted is maybe 15. So my residual value for this one will be negative 4. Now, what you find here is that's what a residual value is. The residual value is literally just the actual minus the predicted, and that's what we're looking at. So how do we calculate the line, the linear, this least squared regression line, and why do we call it least square regression line? So I'm just going to pull up an example, and I really do like this example for you guys to try and get your head around it. Let's just say we've got 1, 2, 3, 4, 5 points, right? And we want to fit a line of best fit on this. Now, this is, you know, just so your axes are along here. Okay, we've got to fit a line of best fit. Well, there's 3 options you could probably do. I mean, you'd probably kind of go like, oh, that would be a line of best fit, right? Or would this be a line of best fit? Or would this be a line of best fit? It's really tricky, you know, quite tricky to tell where your line of best fit is. So we're going to look at this same 5 dots in different scenarios. So let's just give scenario 1 of, let's go with this way, is our line of best fit. And let's look at these 3 dots again, these 5 dots again, 1, 2. So we're going to understand a bit about the concepts of regression lines on this. And let's just say, well, actually, you know what? I reckon best line of best fit would be through here. So what we're trying to actually look at here, guys, just so you do understand, is we're really trying to understand when you go into statistics and you put all your data in, right? Whatever it is. Oh, we can't have W in there. And when you go calc up here, if you go calc regression lin reg, this is the least squared regression line. We're going to understand how the calculator does this, you know, so my X list, my Y list, and what this R value, so, you know, Pearson's correlation, we're going to understand how this actually comes about as well, too, and the strength of that and how that's calculated. So we're going to look at that. And then if I do a scatter plot, let me just do a scatter plot. So we're looking at this here, and we're looking at the scatter plot. So how that's calculated, because the R values sort of calculate off these residuals as well. Anyway, let's go back to this point. So we've got option 1, right? We've got option 2, which kind of takes the averages both, and we're going to have an option 3. And option 3, we're going to have, we've got this dot, this dot, this dot. So this is all the same kind of ones. And this dot. Now, how can we determine which one's the line of best view? I mean, people will be like, oh, well, probably 2, because I mean, it's kind of in between these, it goes there and in between here. But mathematically, we need to sort of always quantify things, okay? So let's give these coordinates some actual, let's give these points some actual values. So then we can start talking about mathematics and have a discussion on, well, which one is the best fit of these 2. So let's just give this point, let's give this point what? We give this point a, let's give this a 2. Let's give this a, I've got to remember my numbers here, 1. I'm going to go, that needs to be at least 2 difference, 3 here, 2, 4, 5, right? So this is the same scale, you know, we're going to use for all of them. Now, let's not worry. That should be 4. Okay, so these are the same scales for all of them. All these points have the same coordinates. So really, if we look at the distance between these two, okay, and we're talking about the residual, we can say that this has a difference of 2, because if we go actual minus predicted, I'm going to go 3 minus 1, has a residual value of 2. This one has a residual, so this one has a residual value of 2, I should say, okay. This one has a residual value of nothing, because it falls right on the line. This one has a residual value of nothing because, I mean, 1 minus 1 is 1. 3 minus 3 is, sorry, 1 minus 1 is 0. 3 minus 3 is 0. And here we have a residual value of 5. Remember, when we're talking about residual values, we're talking about the difference in this gap. Okay, that's what a residual value is. Is there any questions so far before I go on that I need to clarify? You guys got any questions? Feel free to jump in. Still all right? Okay. So this residual is pretty important to sort of understand. This residual value here is 2, right? Okay. So I can say, well, you know, sorry, negative 2, I should say. Now here I can see that, you know, I've got a sum of the residuals of, well, if I add up all these zeros, because this is actual minus predicted, that is 2, that is, well, my total sum of all my residuals, this symbol meaning sum of my residuals, that equals 0. But I mean, if you look at it, you've got one that's 2 and one that's negative 2, but the sum of them's 0. Let's look at the residuals here. Now, obviously, this is the same scale. The residual here would be 1 because it's, you know, my actual minus predicted, and obviously that line's coming at 2. And this one here would be negative 1, right? Okay. This one here is 0, my residual, because it falls on the line, actual minus predicted the same. Here would have 1, and here would have negative 1. Now, if you look at the sum of my residuals again, it equals 0. Right, and this is what the calculator, or one of the problems was when we first tried to get a calculated method to find the line of best fit. They looked at these residual values because really when you want to find the list of best fit, you want to minimize, you know, you want to get a line that minimizes the distance between them all. Let's look at this one. This one, actual minus predicted. This is going to have a value, residual value of negative 2. This one is obviously on the line, so that's going to have a value of 0 because actual and predicted is the same. Actual minus predicted is the same, and actual minus predicted is the same, so it's going to be 0. Actual minus predicted, this would have a value of 2. So here, again, if I look at the sum of all my r's, it's actually going to equal 0. Okay, so, well, what about if I go, well, let's look just how much the positives add up to. Well, the positives here add up to 2. This adds up to 2 as well because they're 2, and this one adds up to 2. But really, you would have thought that 2 is probably the best fit because, I mean, it's kind of like halfway between these lines, you know what I mean? Like here, it's pretty unbiased. You've got one like laying out here and one laying out there. If you just tilted it halfway, you'd say that's pretty well shared between all the points. But this one's not shared. So what we call the least squared residual line. Now, remember we talked about, you're going to understand why it's called, why do we call this least squared regression line, sorry. And why we call it a least squared regression is because we actually look at, it minimizes the sum of the squared values of the residual. So let's look at that. So it minimizes the sum of the squared values of the residuals. So far, we've looked at the sum of just the residuals. So what they realized is why they need to square it was for 2 things. One, your negatives cancel out with your positives. Okay, always. It doesn't really matter where you do it, but you notice it cancels it out. If I do the sum of the squares of my residuals, let's see what happens there. This residual has 2. If I squared that, the square of that is 4. Okay, this residual 0 squared is 0. This is still 0. This is still 0. Negative 2 squared, though, would now become 4. So notice now the sum of my squared residuals is now 16. This one over here, if I square 1, that's just still 1. If I square negative 1, that's 1. 0 is still 0. Positive 1, square that is 1. Negative 1, that should be, sorry, I put a line there. Negative 1 squared is 1. The sum of these squared residuals is 4. Okay, so 4. All right. And if we look at this one again, if I square all my residuals, I'm going to get negative 2 squared is 4. 2 is 4 and 0 is still also the same. So, oh, sorry, this shouldn't be 16. This should be the sum of them. That should be 8 because 4 plus 0 plus 0 plus 0 plus 4 is 8. And the sum of these residuals that are all squared, that will equal 8 as well. Now, what line do we choose? We want to choose the least squared regression line, which really means you want to minimize the sum of the squared values of the residuals. So we're looking for the one that has the least squared. And why we call it least squared is because I want to choose the one that's the least. This one's got 8, this one's got 4, this one's got 8. I want the least. So I'm going to choose this one. That's got the least. And it's the square of the residuals, but we call it the least squared regression line. So really what we're looking at is what the calculator does is it actually squares these. And why we square them, because if we don't, you can hopefully see that you're going to get the same answer. You know, it's going to be out to 0 because no matter what, they're going to be balanced out. So we have to square it to get rid of this negative and positive thing. And also when you do square it, the numbers actually then work a lot better to give you a better fit, as you can see. And that's really where the least squared regression line comes from. So it comes from the sum of the squared residual values. Now, don't get confused. Residual values are actual minus predicted. When we do a least squared regression line, it squares these residual values, and then we add up all the sum of them. Now, I've just used, obviously, 5 data points as an example. I use this one because I think it's a really good example. Students have clicked with it, and that makes sense why we call it a least square regression line, because it's actually choosing the least squares of the residuals, and that makes a line. It makes a regression line. And that's pretty much how the CAS does it. So when you do what your CAS does, when we do this, you know, when we go up here and we go calc regression lin reg, what it's actually doing is it's actually taking all these values and it's trying to take the residual of all these ones, the distance of them, it's squaring them, and it's trying to find the least square of those, and then it plots a line on there for you. And that's what the CAS does. So that's pretty much the chapter A, really, with understanding that. I find that's the hardest part. The only other part that is difficult is literally just make sure you've got this in your book, okay? So, and you need this. So sometimes it can be given to you in words, it can be given to you as symbols, the values, but all you need to know how to use this is really the first thing you need to do is find B, the value of B, and B is the gradient. And then once you've found the gradient, then you can find the y-intercept, which is A. Sometimes some questions will give you the gradient already, so they might already give you the gradient, but then they might give you on top of that the mean for the y and the mean for the x. This is just something you literally have in your reference book. You'll get a question like this and you just plug it in and it will work out for you. This will be a typical show that question where you'll need to figure it out, or you just use your calculator and just literally use the formulas there. So all you're trying to do is you're trying to find in y equals, this is your y-intercept, you know, that's your gradient. You just, sometimes you're given these other values and you can derive them from here. I'm not really going to unpack that because it's just a waste of time in year 12. It's just literally have this in your reference book. This is super key. Copy that down. Make sure you do a couple of questions. You can get them right. If you get them wrong, watch the videos. If you're still getting them wrong, yell out because it's an easy give me point. That's the first chapter. That's pretty much it. The second chapter that we really get into after that, which I don't really want to jump into, I think, yet, when we're looking at 3B, where are we? I'm probably going too much up. The next chapter is quite easy as yeah, so you should be able to know how to do a lin reg, that is 3A. The next subchapter is using regression lines to make predictions. This is pretty damn easy. All we need to do is put in our data points like I've shown you, and you can do a lin reg. Alternatively, it gives you an equation, height and age, and you literally on how much on average does a child grow each year, correct to 2 decimal places? Well, that would be the gradient, right? Because, you know, we're saying each year how much they go up by. I will touch on this because there is a specific way we need to write this. This is very literacy focused. There would be an example that I'll give you guys exactly how to do it, which is like basically for every one of these. So for every year older a child will get, they will grow 10.46 centimeters. So it would be basically like that. How tall is a child perceived to be when they are born? So that would be the y-intercept. We've got to look at the formula here. One thing you want to make sure is don't look at off this, because sometimes this might start at 5, for example. So just be careful. Sometimes you need to figure out what the equation is, but that would be, they're perceived to be 58.22 centimeters. Is the prediction in part 1 example of interpolation? I mean in the data set. Is it within the data set? Well, if you look at the data set starts at 1 year old and it finishes just before 6. So if it is inside the data set, it's called interpolation. If it's outside of the data set, it's called extrapolation. So this is extrapolation because there's no data there to support it. So that's an example of that. That is pretty much most of Chapter 1B. I don't think it's too hard. You put in your data, you do a lin reg, you got to know which one's your x and y axis, which we've already determined with that. And then really it's about using that line to do some predictions. So how can you do that on your CAS? There's a few easy things. You can go calc. As I said, what I tend to do is go calc, regression, lin reg, and notice this copy formula. You can copy this across to Y1 if you like. Okay, hit OK to that. Once that copies that across to the, that will actually copy it to Y1. You can do OK to this. Now I can predict off here. I can just go analyze, trace, and then I can just literally type in like 0, for example, and then it will say, hey, when x equals 0, what's my y value? Well, it says domain because I can't see, but let's just go with 10, 12. What am I up to? 49. Okay, so 56, and it will tell me. Now, if it's notice 0 didn't work, so you need to zoom, out, or you need to do, set your zoom here. So I want to start x at -10, right? And I need to make sure I can see it. That did not change it. My x min at -10. There we go. Now, what is going on with this one? No, it doesn't want to zoom. I do not know what's going on with my calculator. Normally that should work and does it. Alternatively, you can also go back into your into your menu, and then in graphs and tables, you notice it's copied my equation over here. So then I can actually do everything I want with that. And for some reason it's saying invalid syntax, which I do not know why. Y equals, we've got everything in there, so that should be fine, but you should be able to just draw that one too. So because of this equation, right? There we go. So now I should be able to set my zoom -10. I think my CAS isn't right. Now I can not see my Y, so I need to change my Y axis so I can see that to go higher. So let's just go to 1,000. Whoops, that's not 1,000. Hit OK. Now I can see it. Now I can go, hey, analyze GSOLVE. I can do an XY calc, or you can just do trace if you want, and then you can literally just type a number in, and that will do just basically a Y calc for you anyway. So there I can find my actual number there. Alternatively, if I do have my formula, I do know that. I mean, you can edit, you can copy, copy all that, and then you can just put in 0 in here, but it also shows you what your y-intercept is there. And you can do that in main. That's pretty much B, A, and B. Please watch the videos though anyway. C comes to about how we look at residuals. Residuals are a little bit different. When we're looking at residuals, we will look at that in C. But quickly, one thing that you will be doing and on the CAS is, and that is again in statistics, notice when you go calc, regression, lin reg. So we've looked at copying formula 1, copy residuals. We're going to copy residuals to list 3. What that does is that's actually now put the distance of these. So if you look at point 1, this is my first point, 60. Where is 6723? So 6723, let's just put in, so that would be around about here, I think, 6723. There we go. That would be about 6723 by the looks of it. Yep, that one there. Okay, so that's 6723. So that's saying the residual value, actual minus predicted, is about 50. So if you look at the actual predicted for there, it's what's that about? 67. So that's about, what's that about? 72. So that's about 50, you know what I mean? Off there. So that's what it's sort of looking at. So this does the residuals for you. Then if you want to do a residual plot, all you're doing with the plot is you're using the same x-axis. So you're using all the same x values, but you're plotting the difference in the residual values. So now you're just going to go, you're going to do a sketch of a, no, that's not what I want to do. I want to do a calc, regression, lin reg. This is going to be my residual plot that I want to do. I don't want to do a lin reg. I just want to do a residual plot. I want to do a residual plot, which is a scatter plot between list, my X is list 1 and my Y will be now list 3 because that shows the residual values. And if I draw that, ignoring that lin reg line, that shouldn't have came up. That's just because I've done a lin reg previously. So now if I just want to get rid of that lin reg, doesn't matter. Now this shows me my residual values. So this is, if there's a point on a line here, that actually indicates that the residual is pretty much 0. So I'm just going to go back up here and go edit, clear all. So let's just go back to the very first example we did, and we'll put in these points. So we had 2, 1, 2, 3, and we'll do those ones. So we had 2, 1, then we had 2, 3, 2, 3, and then we had 3, 3 by memory. Yep, 3, 3, and then we had 4, 3, 4 for the X, 3 here, and we had 4 and 5. So let's just draw those like that, right? So now if I go analyze calc, regression, lin reg, and we've got our X's and Y's, right? You can see it's chosen the least squared regression line, right, that we proved before. And you know, you can see that's why it's gone for the least squared regression. So we did that. We'll copy the residuals to list 3. So we'll actually look at the residual values now that makes the least squared regression line. Notice the R squared is 0.5. Because, yeah, anyway, it's halfway all the points, which is, anyway, what it's meant to be. So we'll get into that a bit later. So we looked at that one here. We've got that. Now, where is my residuals? Did I not copy them? I'm not. Calc, regression, lin reg. I want to copy my residuals to list 3. Hit OK. Okay, list 3. Why are my residuals? There they are. I'm like, why aren't they coming up? Okay, so now I'm going to do a residual graph, and all we need to do here is keep our X's the same, and we just plot the residuals, and all it shows is a graph of your residuals. So I'm going to do a scatter. I'm just going to change this to list 3, and now that is a residual plot if I plot this. So notice it's showing the residual values. So you can see here, this had a residual value of 1, actual minus predicted. I mean, this here has a scale of 1. If I just zoom out. So you can see they're my residual values now. I mean, we're talking about how far away it is from the line. So really you can just sort of turn your head here a little bit to the left and you can kind of see what the residual value is. So the residual value there is 1. That's got a residual value of -1. This has a residual value of 0. This has a residual value of 1, which we figured out, and this has a residual value of -1. That's 6, A, B, and C in about half an hour for you guys. So I think I did not too bad. But yeah, there is a bit more to it, but that sort of gives you hopefully a good indication of what we're sort of coming up with. And as I said, we're just trying to understand why we call it the least squared regression line, because we're trying to take the residuals, we're squaring the residuals, and we want to find the least sum of those. And that's how a least squared regression line. And that's what a residual is, actual minus predicted. So if it's above the line, it's always going to be positive. Below the line, it's always going to be a negative value. We use lin reg to do predictions, and that's what we really want to do. So I hope that helps. I'm just going to end the recording there, but if you've got any questions, yell out. So the highest point we don't calculate. So the highest point we don't calculate is its residual. I'm not too sure what you mean by that one. Let me just stop this recording. Can you help us with that?